Students, this is an IIT pattern of question. That is, in your IITs you get some passages there, and you need to answer the questions based on that. So it is, J.J. Thomson observed that when light of a certain frequency strikes the surface of a metal, electrons are ejected from the metal. This phenomenon is called photoelectric effect. Right. This is the same thing. This proves the particle nature of light. Only a few metals show this effect under the action of visible light, but many more show it under the action of more energetic ultraviolet light. That is, this ejection of electrons is shown by very few metals. Okay. Now let's see, let's solve the questions. Very few metals by the light of high frequency, the light with the low frequency, whereas some metals require the light with a high frequency. You know that energy is directly related to frequency, right? So more is the frequency, more is the energy. That is, your energy is equal to h nu. That is, the energy is directly proportional to frequency. So your more is the energy, more is the frequency. Now let's solve this question. Which metal is used in photoelectric cell and why? Now students, just I would like to tell you, say if I am taking a metal plate, this is a metal plate on which the light rays strikes. Right, this, and your electron is ejected. What is it required? Now this electron requires to break the force of attraction between itself and the nucleus. Now your every atom has got what? Has got the central nucleus over here and electrons. Now this electron, if you provide energy to the electron, what will happen? This electron moves out. So that energy is called as what? Ionization energy. That is, what is an ionization energy? Ionization energy is equal to the minimum energy required to release the valence electron or the loosely bound electron, right? Now, as we move down the group, what happens? What type of elements form the positive ions? The alkali metals. Now, when we are moving down the group in the periodic table, you must have done in your 10th, what happens? The size increases. Now as the size increases, the force of attraction between the nucleus and electrons decreases, right? So what will happen to the ionization energy down the group? The ionization energy down the group should decrease, right? So it decreases. So students, what type of metals can we use in this thing, for producing photoelectric current? Those which have got low ionization energy, right? If you are using the metal which has high ionization energy, what will happen? You will require a lot of energy to eliminate or release an electron. Now let's come to our question. Which metal is used in photoelectric cell and why? Cesium with lowest ionization energy among alkali metals. Copper being conducting metal. Do we need a good conductor here? No. We just need a metal to start the electric current by ejecting an electron. So this option is ruled out. Lithium being the lightest alkali metal. Do we need this lightness as a characteristic property required for photoelectric effect? No. Silver being anti-corrosive. Do we need this corrosive property? No. So what is the basic property required for photoelectric current? It is the ionization energy. Right? So cesium is the metal usually used in photoelectric bells. Now let's take up this question here. It is, consider the following statements. What are they? Threshold energy, also called work function. What is it? Threshold energy, it is given by h nu 0. Enables the electron to break away from the atom by overcoming the attractive influence of nucleus. Right? What is threshold energy? It is the minimum possible energy required to just remove the electron from an atom. It is an electric current, right? The energy of an individual photon depends on the frequency and the intensity of light beam. Is it correct, students? Does the energy depend on the intensity? No. It depends only on the frequency. Now, so this statement is wrong, right? Because it depends only on the it depends only on the frequency. Right? Now our next question is, frequency of the emitted electron is given by Moseley's equation, or the emitted rays you can say. That is, nu is equal to A into Z minus B. Now what is this thing A here? A is a constant which depends on the nature of the atom or the nature of the metal. Your B is what, students? B is another constant. So Z is the atomic number and A and B are the constants. So can you suggest me what is it? Select the, I'll write it, the correct statements over here. So what all are the correct statements, students? This is the Moseley's equation. We discussed this in our previous session. This is the frequency of the X-rays which were produced, and what he did, he plotted a graph between square root of frequency and atomic number and got a straight line. And B is constant for different series. Say for K series it is a constant, it has a constant value. L series, it is again a constant value. So what are the correct statements here? It is A and C, right? So this is the way you need to analyze each and every statement. Just see this, what it is saying. When a certain metal was irradiated with light of frequency 1.6 into 10 to the power minus 16 Hertz, right? The photoelectrons emitted had twice the kinetic energy as did photoelectrons emitted when the same metal was irradiated with light of frequency 1 into 10 to the power 16 Hertz. Thus, the threshold frequency of metal is. That is what it is saying. I'll explain you this question, that say if a metal, this is a metal, right? Now what is happening? This is irradiated with a light. And students, what is the frequency of light? That is equal to 1.6 into 10 to the power 16 Hertz. Now due to which what has happened? Electron is ejected and it has got some kinetic energy, right? This is your one case. And it is saying that the kinetic energy is double. Say the same metal is irradiated with a light of frequency nu is equal to 1 into 10 to the power 16 Hertz. Then again an electron is emitted and this has some kinetic energy. Now what can we take is that this kinetic energy with a frequency 1.6 is double the kinetic energy, right? The first one. So we can say that the kinetic energy 2 is equal to twice of kinetic energy 1, right? Or we can write here as K2 is equal to K1. Now students, what is the expression for this kinetic energy? We can solve it in a page here separately. What is the expression? What was that? It is saying that the frequency, will take it as nu2, is equal to 1.6 into 10 to the power 16 Hertz, and K2 is equal to K1, whereas your frequency 1 is equal to 1 into 10 to the power 16 Hertz. Now what does it say? Now your K2 is equal to 2K1. Now what is the expression for this? Your kinetic energy is equal to the h nu minus h nu 0. That is the total frequency or the total energy minus the threshold energy, right? So we can say as K2 is equal to h nu 2 minus h nu 0, and likewise your K1 is equal to h nu 1 minus h nu 0, right? Now what is your K2 equal to? K2 is equal to 2K1, right? Now can we equate the two? That is K2 is h nu 2 minus h nu 0 nu naught is equal to 2 into h nu 1 minus h nu naught, because this is the value for K1, right? Now I hope you can solve this. You are in. Now what can we do? This is for K1, this is not upon K1, right? So this would be, can we write it as h nu 2 minus 2h nu 1, and that is equal to h nu naught minus 2h nu naught. Conversely, 2h nu 1 minus h nu 2 is equal to 2h nu naught minus h nu naught, or h nu naught is equal to 2 multiplied by what? Multiplied by your h value. You can take out h as common, right? and it would be what can you make it? 2h minus h, and this will give you what? This will give you h multiplied by, it would be 2 nu1 minus nu2. Got my point? How I got this? If I break this equation, what I'll get? I'll solve it here. I want everything to be crystal clear here. Say 2h1 is 2h, minus h, right, multiplied by 2 nu1 minus nu2, right? So I've done it like this, and I will get what here? I am getting h into this. This h will get cancelled, and nu naught will be equal to 2 into nu1. What was nu1, students? Nu1 was 1 into 10 to the power 16 minus 1.6 into 10 to the power 16. What am I going to get here? It was 1.6, right? This. So I am getting 2 minus 1.6. That will be what? That will be 0.4 into 10 to the power 16, right? Hertz. Or the threshold frequency, that is nu naught, will be equal to 4 into 10 to the power 15 hertz. Got my point? So what will be the answer of this, students? The answer of this question would be 4 into 10 to the power 15 hertz. I hope this question is clear to you. It was a very simple question actually. This is not a very difficult one. You have to just make equations. Let's take up our next question. Yeah, it is. When would the wavelength associated with an electron be equal to the wavelength associated with a proton? Now students, do you remember the Broglie equation? It is lambda is equal to h upon mv. So that is, your lambda is inversely proportional to mv. Now can I write it like this? Lambda E is equal to mpvp, upon lambda p, that is equal to what? MEVE. That is, your lambda p is equal to h upon mpvp. Lambda E is equal to h upon MEVE. Now what is it saying? The wavelength has to be equal. That is, your lambda E should be equal to lambda p. Right? It means what? Your MEVE should be equal to mpvp. Now what is the mass of the electron, or what is the mass of the proton here? It is mass of the electron is 1 by 1835 times of mass of proton, right? Multiplied by velocity, and mp is 1 and vp. So can we say that when it would be equal? It would be equal when the velocity of electron becomes equal to 1835 times of a proton. Can I write it like this? That is, your velocity of electron is equal to, what is mass of proton? It is 1. That is equal to 1835 times of velocity of proton. Right? So what will be a correct answer here? It would be the velocity of electron is 1835 times that of proton.